Imagine you're walking through a desert. Not just any desert, but the Sahara, where sand dunes stretch endlessly under a relentless sun. You're miles from anywhere when your foot catches on something hard. You brush away the sand and find a smooth stone surface. Carved into it are symbols, patterns, too precise to be natural, too weathered to be recent. You keep digging and realize this isn't just a stone. It's a foundation, a wall, the remnants of something built by intelligent hands. Now here's where it gets strange. You send samples to a lab. Carbon dating, geological analysis, the works. The results come back and they don't make sense. These ruins aren't thousands of years old. They're not tens of thousands or even hundreds of thousands. The rock formations surrounding them, the geological layers they're buried in, suggest they're 50 million years old. 50 million. That's before humans, before apes, before anything remotely like us walked this planet. Your first instinct would be to assume you made a mistake, or the scientists made a mistake. Because that's impossible, right? We're the first, we're the only. Humans are the only species in Earth's entire 4.5 billion year history to build cities, develop technology, create civilization. That's what we've always believed. That's what every textbook tells us. That's what seems obvious. But what if it's not true? What if intelligent life arose on this planet millions of years before us and we just don't know it? What if there were others who looked up at the same stars, asked the same questions, built their own version of civilization, and then vanished so completely that almost nothing remains? It sounds like science fiction, like something from Doctor Who, which actually is where part of this story begins. But it's also a serious scientific question that's been puzzling researchers in recent years. Because the more we learn about Earth's deep history, the more we realize how little we actually know. And the more we understand about fossilization, geology, and deep time, the more we have to confront an unsettling possibility. If an industrial civilization existed on Earth millions of years ago, would we even be able to detect it? This question has a name. It's called the Silurian hypothesis, named after an ancient race of reptilian humanoids from that British sci-fi show. But don't let the pop culture reference fool you. This is real science, published in legitimate journals, debated by actual climatologists and geologists. The hypothesis doesn't claim that ancient civilizations definitely existed. It asks something more subtle and more profound. How would we know if they had? What evidence would survive tens or hundreds of millions of years? What would we be looking for? And here's the kicker. Have we already found it and just not recognized it for what it is? See, humans have only been doing anything you could call civilization for about 12,000 years. We've only been industrial for about 200. That's nothing. Less than an eye blink in geological terms. Earth has been around for 4,500,000,000 years. Complex life has existed for over 500 million. That's an enormous window of time. Millions of centuries where something could have happened. Something we'd never see coming because we're not even looking for it. We assume we're first because we can't find evidence of anyone else. But absence of evidence isn't evidence of absence. Especially when you're looking back across timescales so vast that entire mountain ranges rise and erode to nothing, where continents drift thousands of miles from where they started, where the ocean floor gets completely recycled every 200 million years, dragged down into Earth's mantle at subduction zones, melted and reformed. If you're using this video to fall asleep, perfect. That's exactly why I make them. Subscribe if you want more and tell me where you are and what time it is. I love checking comments and seeing Tokyo at sunrise, Melbourne at midnight, Detroit at dinner time, all at once. There's something comforting about that. All of us scattered across the world listening to the same strange questions about deep time. So tonight we're going on a journey, not through space but through time. We're going to explore what might be hiding in Earth's ancient rocks. We'll look at mysterious chemical signatures that don't quite make sense, strange spikes in the geological record that could be natural or could be something else. We'll ask what would survive if our own civilization vanished tomorrow and examine whether we'd even recognize the traces of industrial activity from 100 million years ago. This is a story about deep time, about the limits of knowledge, about how the universe might be stranger than we dare to imagine. So get comfortable, relax. Let your mind drift back through the eons, because we're about to question something fundamental. Something we've never really doubted before. What if we are not the first? Now, before we go any further, we need to talk about what this hypothesis actually is. Because the name alone probably sounds ridiculous to you. The Silurian hypothesis. It sounds like something from a late-night conspiracy theory forum or maybe a rejected science fiction novel premise. And honestly, that's exactly where the name comes from. But the science behind it? That's deadly serious. The hypothesis was formally proposed in 2018 by two scientists who, between them, have about as much credibility as you can get in their fields. Gavin Schmidt, he's the director of NASA's Goddard Institute for Space Studies. This isn't some fringe researcher working out of his garage. This is one of the most respected climate scientists on the planet. Someone who literally models Earth's climate systems for NASA. The other half of this duo is Adam Frank, an astrophysicist from the University of Rochester who specializes in the life cycle of stars and planets. Together they published a paper that would ask one of the strangest questions in modern science. Could we actually detect evidence of a prior industrial civilization in Earth's geological record? The name comes from Doctor Who. Specifically, it references the Silurians, a race of intelligent reptiles who, in the show's mythology, evolved on Earth millions of years before humans and built an advanced civilization before going into hibernation. Schmidt and Frank needed a catchy name for their thought experiment, and that's what they picked. They're not claiming lizard people existed. They're not saying they believe there was a prior civilization. They're asking a much more subtle, much more scientifically interesting question. If there had been an industrial civilization on Earth millions of years ago, would we be able to find it? Think about that for a second. Not could there have been one. Not is there any evidence for one. But would we even know how to look? Would we recognize the signs? Would anything even survive for us to find? This is what makes the Silurian hypothesis so fascinating. It's not pseudoscience dressed up in academic language. It's genuine scientific inquiry into the limits of our knowledge and our detection capabilities. It's the kind of question that sounds crazy until you actually think about it, and then you realize it's actually profound. Here's why scientists would even ask something that seems so outlandish. We're living in a moment where humanity is leaving very specific signatures on the planet. Chemical signatures, geological signatures, radiological signatures. We're changing the composition of the atmosphere, depositing synthetic materials that will persist for millions of years, triggering what some scientists call the sixth mass extinction event in Earth's history. Future geologists, whether they're human or something else entirely, will look at rock layers from our time and see something radically different from everything that came before. They'll see the Anthropocene, the age of humanity written in stone. But how long will those signatures remain detectable? That's the question Schmidt and Frank were really asking, not because they believe in ancient lost civilizations, but because understanding what evidence would survive helps us understand our own impact on the planet. If you're trying to model long-term climate change or understand how planetary systems respond to rapid industrialization, you need to know what traces survive and for how long. By the way, I'm curious where you all are right now as you're listening to this. Drop a comment and let me know where you're watching from and what time it is for you. Are you drifting off to sleep in Tokyo at 2 a.m? Having breakfast in London? Unwinding after work in Sao Paulo? There's something fascinating about all of us, scattered across the world, thinking about the same deep questions about time and existence. So back to the hypothesis. The paper that Schmidt and Frank published wasn't claiming anything extraordinary. It was doing something more interesting. It was methodically working through what traces an industrial civilization might leave, and how long each of those traces would remain detectable in the geological record. They started with the most obvious stuff: cities, roads, buildings, all the physical infrastructure of civilization. You'd think this would last forever, right? Look at the pyramids. They've been standing for 4,500 years. Surely concrete and steel would survive for millions of years, leaving obvious traces of whoever built them. But here's the thing. 4,500 years is nothing. Geologically speaking, it's a blink. The pyramids seem permanent to us because human timescales are measured in decades or centuries, but geological timescales are measured in millions of years, and on those timescales, even the most solid human constructions are as temporary as sand castles at high tide. Think about what happens to a city when humans abandon it. Within decades, vegetation starts breaking apart roads and buildings. Within centuries, most structures have collapsed. Within thousands of years, even the foundations are being broken down by freeze-thaw cycles, root systems, chemical weathering. Within millions of years, plate tectonics have recycled the entire land surface multiple times over. That city has been subducted into the mantle, melted, and redeposited as new rock somewhere else entirely. The Earth is not a museum, it's a recycling system, an incredibly efficient one that's been operating for 4.5 billion years. The planet destroys evidence as fast as it creates it, grinding and melting and mixing everything back into the geological cycle. So if physical structures wouldn't survive, what would? This is where Schmidt and Frank's analysis gets really interesting. They started looking at more subtle signatures, things that might persist even when the physical objects are long gone. Chemical signatures, for instance. An industrial civilization would burn massive amounts of fossil fuels, depositing specific isotopes of carbon into the atmosphere and oceans. It would mine rare earth elements and concentrate them in ways that don't happen naturally. It would create synthetic molecules that don't exist in nature, plastics and pesticides and pharmaceutical compounds that might leave traces in the sedimentary record. Radioactive signatures too. If a civilization developed nuclear technology, it would leave behind isotopes with very specific half-lives and ratios. These would be detectable for millions of years, maybe longer, depending on what exactly was produced and where it ended up. Temperature spikes. A rapid industrialization would cause sudden warming, which would show up in ice cores, sediment layers, and fossilized pollen records as an abrupt shift in climate. This would be visible even hundreds of millions of years later if you knew what to look for: mass extinction events. The rapid environmental changes caused by industrialization would likely drive many species extinct, creating a distinct layer in the fossil record where biodiversity suddenly crashes. The question Schmidt and Frank were asking is this: if you're a geologist 100 million years in the future, looking at rocks from our time, what would you see? And more importantly, if there had been another industrial civilization 100 million years in our past, what would we see now? This is why the hypothesis matters, not because it's claiming ancient aliens or lost Atlantean super-civilizations, but because it forces us to think carefully about how geological processes preserve and destroy information. It makes us question our assumptions about what we would recognize and what we might miss. And here's the uncomfortable part. The answer Schmidt and Frank arrived at is that we probably couldn't detect a prior civilization if it had existed more than about 4 million years ago, maybe 10 million if we're lucky, and they left particularly strong signatures in exactly the right places. 4 million years. That sounds like a lot. But Earth is 4.5 billion years old. Complex life has existed for at least 600 million years. If we can only see back 4 million years with any confidence, That means we're potentially blind to 99% of Earth's history when it comes to detecting industrial civilizations. Think about that. We could only see the most recent 0.1% of Earth's history. Everything before that is essentially invisible to us, at least when it comes to detecting the kind of signatures that an industrial civilization would leave. This doesn't mean there was a prior civilization. The hypothesis isn't claiming that. But it does mean we can't definitively rule it out based on lack of evidence, because the evidence might simply not survive long enough for us to find. That's what makes this such a good scientific question. It's not asking us to believe something extraordinary. It's asking us to carefully examine the limits of what we can know, to understand how information degrades over geological time, to think about what traces we're leaving and how long they'll last. And in doing so, it opens up some genuinely unsettling possibilities. Not because they're likely, but because they're not impossible. Because the absence of evidence in this case really isn't evidence of absence. So let's dig deeper into deep time itself and start to understand just how vast Earth's history really is. Here's the thing about time that nobody really prepares you for. We think we understand it because we live through it every day. Seconds, minutes, hours, years. We measure our lives in decades. We think of ancient Rome as incredibly old, and it was. 2,000 years is a long time by human standards. But Earth doesn't think in terms of decades or millennia or even millions of years. Earth thinks in billions. And when you're trying to understand whether another civilization could have existed before us, you first have to wrap your mind around just how much time we're actually dealing with. So let's do something that geologists call the cosmic calendar. Let's compress all of Earth's history, all 4.5 billion years of it, into a single year. January 1st at midnight, the Earth forms from a disk of dust and gas orbiting our infant sun. It's molten, chaotic, being constantly bombarded by asteroids and comets. For the entire month of January and most of February, Earth is basically hell. A ball of liquid rock slowly cooling, constantly being reshaped by impacts. The moon forms when a Mars-sized object slams into Earth around mid-January. The debris from that collision eventually coalesces into our satellite. By late February, things have cooled enough that the first solid crust forms. By March, there's liquid water, actual oceans forming in the basins between volcanic mountain ranges. And somewhere in those oceans, probably in March or early April, life begins. We're not sure exactly when or how, but chemical reactions in those ancient seas create the first self-replicating molecules, the first primitive cells, single-celled organisms that would look like nothing to your eyes, but they're life. They're the beginning of everything. For the next 6 months, from April through September, that's all there is. Single-celled organisms, bacteria and archaea floating in the oceans, slowly, incrementally changing the chemistry of the planet. Some of them learn to photosynthesize, to turn sunlight into energy. This is revolutionary because it produces oxygen as a waste product. And oxygen, which we think of as life-giving, is actually toxic to most of the organisms alive at that time. The Great Oxygenation Event happens around July in our cosmic calendar. It's Earth's first major pollution crisis, caused by life itself. Oxygen levels rise, most of the planet's organisms die off, but a few survive, a few adapt, and suddenly there's a new resource to exploit. Still, for months after that, nothing particularly dramatic happens. Evolution proceeds, but slowly. More bacteria, more single-celled organisms, different strategies for survival, but nothing you could see with your naked eye. The entire summer passes. August, September, October. Still just microscopic life floating in the oceans. Then, around mid-November, something incredible happens. The first multicellular organisms appear. Cells that cooperate, that stick together, that specialize for different functions. These are still incredibly simple, mostly just clumps of cells, but they're the beginning of complex life. By late November, you start seeing the first real animals, the Ediacaran fauna, weird soft-bodied creatures that look like nothing alive today. Some resemble ferns, others look like quilted mattresses. They live on the ocean floor, filter feeding, doing whatever strange things they did in that ancient sea. December 1st marks the beginning of the Cambrian explosion. Suddenly, in evolutionary terms, the oceans fill with diversity. Animals with shells, with eyes, with predatory lifestyles. The first fish appear, the first arthropods. This is the moment when life as we would recognize it really begins. But we're talking about December 1st. We still have 31 days left in our year. December the 5th, plants colonize the land. Before this, continents were barren rock. But now mosses and simple plants begin spreading across the shorelines. By December 8th, the first insects follow them onto land. December 10th brings the first forests, massive tree ferns and primitive conifers, creating ecosystems that have never existed before. Coal deposits that power our modern world. Most of them form from forests that grew between December 10th and December 15th. Trees that lived and died and were buried in swamps, compressed over hundreds of millions of years into the black rock we burn today. December 13th, the first amphibians crawl out of the water. Fish with legs, basically, capable of surviving on land but still tied to water for reproduction. December 15th brings the first reptiles, animals that have fully solved the problem of living on land. They lay eggs with shells. They have scaly skin that doesn't dry out. They're free to colonize the continents. Then December 18th, disaster. The Permian extinction, the worst mass extinction in Earth's history. Volcanic eruptions in what is now Siberia pump so much carbon dioxide and sulfur into the atmosphere that the climate goes haywire. Ocean chemistry changes. Oxygen levels plummet. About 96% of all marine species die. 70% of land species die. Life comes closer to complete extinction than at any other time in its history. The world becomes a graveyard. But life recovers. It always recovers, given time. By December 20th, a new world order emerges. The age of dinosaurs begins. For the next week, December 20th through December 26th, reptiles dominate everything. Enormous sauropods browsing on treetops, theropods hunting in packs, pterosaurs ruling the skies, marine reptiles like mosasaurs and plesiosaurs owning the oceans. For 6 full days of our calendar year, which represents about 165 million actual years, dinosaurs are the undisputed masters of Earth. December 26th, late evening, another catastrophe. An asteroid 6 miles wide slams into what is now Mexico. The impact creates a crater 110 miles across. The energy release is equivalent to billions of nuclear weapons. Global firestorms, tsunamis that sweep across continents. So much dust and debris thrown into the atmosphere that sunlight is blocked for years. Plants die, herbivores die, carnivores die. The dinosaurs, after 165 million years of dominance, are gone in what amounts to a few hours on our cosmic calendar. But tiny mammals that had been living in the dinosaurs' shadows, they survive. Creatures no larger than rats, hiding in burrows, eating insects and seeds. When the dust clears, they inherit an empty world, and they explode into every available niche. Within days on our calendar, which represents millions of actual years, mammals diversify into forms ranging from whales to bats to primates. December 31st arrives. We're in the final day of Earth's year. At 6 a.m. on December 31st, the first great apes appear. At 11:40 p.m., still December 31st, the genus Homo evolves. Human ancestors walking upright, using tools but not yet modern. At 11:58 p.m, anatomically modern humans appear in Africa. We've existed for about 2 minutes of Earth's 4.5 billion year calendar. At 11:59:46 p.m, 14 seconds before midnight, recorded human history begins. The pyramids of Egypt, all of ancient Rome, the entire medieval period, the Renaissance, the Industrial Revolution, both world wars, the space age, the internet, everything you think of as human civilization happens in the last 14 seconds before midnight on December 31st. Let that sink in. Everything we've ever built, every empire that's ever risen and fallen, every book ever written, every song ever composed, every human being who has ever lived, all of it compressed into 14 seconds out of a full year. We are incredibly, almost incomprehensibly new. Now, here's why this matters for our question about prior civilizations. Look at all that time. All those millions and millions of years between December 1st and December 30th. Multiple complete turnovers of life, multiple mass extinctions, each one wiping the slate clean and forcing evolution to start over. The Ordovician extinction on December 7th, the Devonian extinction on December 11th, the Permian extinction on December 18th, the Triassic extinction on December 22nd, the Cretaceous extinction on December 26th. Earth has experienced at least 5 major mass extinctions, where more than 75% of all species disappeared, plus dozens of smaller extinction events. Each one represents a complete reset of the biosphere. Each one destroys the dominant life forms and creates opportunities for something new. Between these extinctions, different forms of life absolutely dominated for time periods that make human civilization look like a blink. The age of fish lasted about 50 million years. The age of reptiles lasted 165 million years. The age of mammals has lasted about 66 million years so far and counting. But here's what really matters. In those vast stretches of time, evolution tried countless experiments. Body plans that succeeded for millions of years then vanished. Ecological strategies that worked until they didn't. Intelligence has evolved multiple times, independently in different lineages. Octopuses developed complex problem-solving abilities. Certain dinosaurs, especially the raptors, showed signs of sophisticated pack-hunting behavior that requires coordination and communication. Some prehistoric marine reptiles had brain-to-body ratios approaching those of modern dolphins. Intelligence isn't rare in evolutionary terms. It's just one strategy among many, and it's been tried before, in different forms, in different ages. The question the Silurian hypothesis asks is simple but profound. In all those millions of years, in all those different ages dominated by different forms of life, could intelligence have gone one step further? Could it have developed technology? Could it have built a civilization? Our perspective is ridiculously limited. We think of time in terms of human generations. 100 years seems long. 1,000 years is ancient. But Earth has been here for 4.5 billion years. Complex life has been here for over 500 million years. For most of that time, the planet looked completely alien. Different continents in different positions, different atmospheres with different chemistries, different animals filling ecological niches that don't even exist anymore. What could have happened in those vast spaces between the mass extinctions? What could have risen and fallen in the 50 million years between the Ordovician and Devonian? What could have built and been destroyed in the 120 million years between the Permian and Cretaceous extinctions? We've explored a tiny fraction of Earth's rock record. Most of it is buried miles deep, or destroyed by plate tectonics, or sitting on ocean floors we've barely mapped. The rocks don't remember everything. In fact, they forget almost everything. Fossilization is incredibly rare. Most organisms that ever lived left no trace whatsoever. Entire ecosystems have come and gone without leaving a single fossil we've found. So if something existed for even a few million years, which is nothing in geological time, and then disappeared, what would remain? That's the question that should keep you up at night. Except we're making content to help you sleep, so maybe let it gently trouble your dreams instead. Because when you really understand deep time, when you really internalize how much history this planet has, you realize something humbling. We're not the culmination of anything, we're just the current experiment, and the Earth has run millions of experiments before us. Here's a question that should keep you awake, or maybe put you to sleep in the most unsettling way possible. If our entire civilization collapsed tomorrow, if every human vanished and 100 million years passed, what would survive? What would geologists of some future intelligent species find when they drilled through the rock layers that used to be our present day? The answer is going to surprise you, and it's going to make you realize just how profound the Silurian hypothesis really is. Let's start with something that sounds obvious, but actually isn't. Fossils are rare. Extraordinarily, bizarrely, almost impossibly rare. We tend to think of the fossil record as this comprehensive archive of ancient life, like Earth kept detailed records of everything that ever existed. But that's not even remotely true. Here's the reality. Of all the organisms that have ever lived on Earth, and we're talking about trillions upon trillions of individual creatures across billions of years, less than 0.1% left any fossil trace whatsoever. That's not a typo. 99.9% of everything that ever lived died and vanished without leaving a single trace in the rock record. Think about that for a second. Entire species that existed for millions of years, that numbered in the billions, that dominated their ecosystems. Gone. Completely erased from history. The only reason we know they existed at all is because we can infer their presence from the species that came after, from the ecological niches that show something must have been there, from the evolutionary gaps that make no sense unless some missing link filled them. So why is fossilization so rare? Because everything has to go perfectly, and I mean everything. When an organism dies, the default outcome is decomposition. Bacteria, fungi, insects, scavengers, they all want those nutrients. A dead animal on the surface is going to be reduced to scattered bones within weeks. Those bones will be broken, scattered, bleached by the sun, broken down by acid rain. Within a few years they'll be fragments. Within a few decades they'll be dust. For fossilization to occur, you need burial. Fast burial. The organism needs to be covered by sediment before decomposition destroys it. This happens in very specific environments. River deltas, lake bottoms, ocean floors, volcanic ash falls, tar pits. Places where sediment is actively accumulating, where bodies get buried quickly and deeply enough that oxygen can't reach them to fuel decomposition. But even burial isn't enough. You need the right kind of sediment. Too coarse and water will flow through it, carrying bacteria and oxygen. Too acidic and it'll dissolve the bones. Too much pressure and the fossils will be crushed. The chemistry has to be perfect for mineralization to occur, for the calcium in bones to be replaced atom by atom with more stable minerals that can survive for millions of years. And even then, you're not done. The fossil has to survive for millions of years without being destroyed. It can't be buried so deep it gets melted by Earth's heat. It can't be uplifted and eroded away. It can't be dissolved by groundwater or crushed by tectonic forces. It has to remain in that narrow zone where it's preserved but not destroyed, protected but not obliterated. And finally, after millions of years of survival against impossible odds, it has to be found. It has to be exposed by erosion at exactly the right time when there's a human around to notice it. And that human has to recognize it as a fossil, excavate it properly, and preserve it before weather destroys it again. When you lay out all these requirements, the miracle isn't that fossilization is rare. The miracle is that we have any fossils at all. Now here's where it gets really interesting. The conditions that favour fossilization are incredibly biased. Aquatic organisms fossilize way better than terrestrial ones. Things with hard shells and bones fossilize better than soft-bodied creatures. Small organisms that live in the right environments fossilize better than large, rare animals that live in the wrong places. This creates enormous gaps in our knowledge. We have beautiful fossils of ancient clams and snails that lived on shallow sea floors. We have almost nothing from the insects that lived in tropical rainforests, even though those insects probably vastly outnumbered the clams. We have good fossils of many dinosaurs because some of them died in the right places, river channels and coastal plains where sediment was accumulating. We have terrible fossils of their contemporaries that lived in mountains and forests, where erosion dominates and sediment doesn't accumulate. The fossil record isn't a comprehensive archive. It's a tiny, biased, incredibly fragmentary sample of ancient life. We're looking at less than 0.1% of what actually existed, and that 0.1% is heavily skewed toward organisms that lived in very specific environments. So let's apply this to our civilization. Imagine humans vanish tomorrow. All 8 billion of us just disappear. What happens to our stuff? Your house starts falling apart immediately, without maintenance. The roof develops leaks within a few years. Water gets in, mold grows, wood rots, metal rusts. Within 20 years, your house is a ruin. Within 50 years, it's a pile of debris. Within 500 years, it's a mound of dirt with some rust stains and maybe a few ceramic tiles. Cities fall faster than you'd think. Without humans to maintain them, nature takes over with shocking speed. Tree roots crack pavement. Water infiltrates buildings. Freeze-thaw cycles shatter concrete. Steel corrodes. Glass breaks. Within a few centuries, our greatest cities would be unrecognizable. Within a few thousand years, they'd be forests and wetlands with barely visible ruins underneath. But what about the big stuff? The really impressive structures? The pyramids, the Great Wall, major dams and bridges. Surely those would last millions of years. No, they wouldn't. Because you're not just fighting decay. You're fighting geology. Earth's surface is in constant motion. Continental plates shift. Mountains rise and erode. Rivers change course. Coastlines advance and retreat. The landscape you see today won't exist in a million years. It will have been completely reworked by geological processes. Mountains erode at rates of about 0.1 to 1 millimeter per year. That doesn't sound like much, but over a million years, that's 100 to 1,000 meters of rock removed. Entire mountain ranges can be eroded flat in 10 million years. Your concrete dam, your steel skyscraper, they'll be ground to nothing long before that. And if they somehow avoid erosion, if they get buried instead of being worn away, then they face a different fate. Burial means heat and pressure. Bury something a few kilometers deep and it'll be heated to hundreds of degrees. The pressure will crush it, metamorphose it, turn it into something unrecognizable. Your city becomes a thin layer of strange minerals in a metamorphic rock. Your technology becomes chemical anomalies that nobody would recognize as artificial. But what about plastics? We're told plastics last forever. They're polluting the oceans, filling landfills. Surely they'd survive for millions of years. Not really. Plastics are organic polymers, long chains of carbon-based molecules. They're more stable than wood or flesh, sure, but they're not immune to breakdown. UV radiation from sunlight breaks down surface plastics in decades. Buried plastics last longer, but over thousands of years, bacteria evolved to eat them. We're already seeing this happen with modern bacteria that can digest certain plastics. Over millions of years, every plastic ever made would be decomposed. The carbon would be recycled into the environment, At best, you might get some unusual chemical signatures in rock layers, slightly elevated concentrations of certain organic molecules, but no plastic bottles, no recognizable artifacts, just faint chemical echoes that could easily be mistaken for natural processes. What about metals? We've produced billions of tons of steel, aluminum, copper. Surely vast metal deposits would survive. Again, no. Metals corrode. Iron rusts back into iron oxide, basically becoming ore again. Aluminum oxidizes. Copper corrodes into green minerals. All the refined metals we've created want to return to their natural oxidized states. That's what corrosion is. The universe erasing our work, returning purified metals to their stable forms. Underground metal deposits might last longer, but over millions of years groundwater would find them. Dissolved oxygen would corrode them. Geological processes would disperse the resulting minerals. Instead of a concentrated mass of refined metal, you'd get a slightly anomalous distribution of metal oxides in the rock record, noticeable if you were specifically looking for it, but easily attributed to natural hydrothermal processes if you weren't. Here's the really disturbing part. The best preserved parts of our civilization won't be our greatest achievements. They won't be our cities, our monuments, our technology. They'll be our garbage. Ceramics last. Pottery shards survive for millions of years because they're already basically rocks. We've fired clay at high temperatures, turning it into a stable mineral form. Those ceramic coffee mugs you've got in your cupboard, they'll outlast everything else you own. But individual pottery shards scattered across a landscape wouldn't be recognized as artificial unless someone was specifically looking for them. They'd be tiny fragments mixed in with natural rocks, easily overlooked or attributed to natural processes. The fossil record of our civilization would be bizarrely biased. Future geologists might find good evidence of our domestic chickens, because we've bred billions of them, and their bones are filling landfills in conditions that favour fossilization. They might find excellent fossils of our rats and pigeons, the urban species that thrive in our cities and die in our sewers, where burial conditions are good. But evidence of our technology, our culture, our intelligence, that would be extraordinarily sparse. A few weird chemical signatures, some unusual mineral distributions. Maybe, if they were very lucky, a few fossilized chicken bones showing evidence of selective breeding. Some ceramic fragments that look suspiciously regular. Chemical traces of industrial processes in ice cores or rock layers. Would that be enough to prove an ancient civilization existed? Or would it just look like natural variations? Unusual, but not impossible geological processes, interesting anomalies that don't quite prove anything. That's the fossilization problem. And it's why the Silurian hypothesis is so unsettling. Because if we vanished today, in 100 million years, there would be almost nothing left. Future geologists would have to be incredibly careful, incredibly thorough, and incredibly lucky to detect that we'd ever existed at all. And that means if some other civilization existed 100 million years before us, we'd face exactly the same challenge. We'd be looking for traces so faint, so ambiguous, so easily confused with natural processes that we might miss them entirely, unless we knew exactly what to look for. Unless we understood what chemical fingerprints an industrial civilization must leave behind. And that's where our story goes next. So you're looking for evidence of ancient civilizations. You're thinking, okay, buildings decay, metal rusts, even the pyramids won't last forever, but surely something survives, right? Some artifact, some structure, some clear sign that intelligence was here. But what if you're looking for the wrong thing? What if the real evidence isn't in what ancient civilizations built, but in what they changed? Not the structures they left behind, but the chemistry they altered. Not the monuments, but the molecules. Think about what our civilization is doing right now to the planet's chemistry. We're not just building things. we're fundamentally altering the atmospheric composition, the ocean chemistry, the very isotopic ratios that define Earth's chemical baseline. And these changes, they're getting locked into the geological record layer by layer, year by year, creating a signature that could persist for millions of years after every last trace of our cities has crumbled to dust. This is the concept of chemical fingerprints, and it might be the only way to detect a truly ancient industrial civilization. Let's start with the most obvious one: carbon. Not just any carbon, but specifically the ratio between carbon-12 and carbon-13, two isotopes that exist naturally in the environment. Plants preferentially absorb the lighter carbon-12 during photosynthesis, which means fossil fuels, being ancient plant material, are enriched in carbon-12 compared to carbon-13. When we burn coal, oil, and natural gas, we're releasing massive amounts of carbon-12 into the atmosphere. This shifts the global carbon isotope ratio in a way that's completely unprecedented in natural Earth processes. Scientists can measure this shift in ice cores, in tree rings, in sediment layers. The beginning of the Industrial Revolution shows up as a distinct spike in atmospheric carbon-12. It's so dramatic, so clear, that geologists in the distant future would see it instantly, even if they had no idea what caused it. They'd know something weird happened, something that pumped light carbon into the atmosphere at rates that don't match volcanic activity, don't match normal decomposition, don't match anything in the natural carbon cycle. But here's the question that should keep you up at night. Would a similar spike from 100 million years ago still be visible? Would it survive the mixing and recycling of Earth's carbon through oceanic absorption, volcanic outgassing, the slow churning of the rock cycle? Maybe, maybe not. The signature would be diluted, smeared across thousands of years of sediment, but it might still be there, a subtle anomaly waiting for someone to look close enough. Then there's nitrogen. Our civilization has done something to nitrogen chemistry that's arguably even more dramatic than what we've done to carbon. We've learned to fix atmospheric nitrogen, turning inert N2 gas into reactive compounds we can use as fertilizer. The Haber-Bosch process, invented in the early 20th century, has fundamentally altered the global nitrogen cycle. We now fix more nitrogen industrially than all natural processes combined. That's not a small thing. That's a complete transformation of one of the planet's fundamental biogeochemical cycles. And it leaves a signature. Synthetic nitrogen fertilizers have a distinctive isotopic ratio, different from naturally fixed nitrogen. As this synthetic nitrogen washes into rivers, lakes, and oceans, it changes the nitrogen isotope ratios in sediments. Researchers have already detected this shift in lake sediments from the past few decades. It's clear, measurable, and entirely artificial. An ancient civilization that developed intensive agriculture would likely have faced the same problem we did. How do you feed billions of people? You need nitrogen fertilizer, and if they solved it the way we did, through industrial nitrogen fixation, they would have left the same kind of isotopic signature in whatever sediments were being deposited during their industrial age. But wait, there's more. Let's talk about something that didn't exist anywhere on Earth until humans invented it. Plastics. Every year we produce over 400 million tons of plastic. Most of it ends up in landfills or the ocean, where it slowly breaks down into smaller and smaller pieces, microplastics, then nanoplastics, eventually just molecules dispersed through the environment. These plastic molecules are remarkably stable. They don't biodegrade easily. They resist chemical breakdown. And they have a unique molecular signature that doesn't exist in nature. Long after every plastic bottle, every shopping bag, every synthetic fabric has broken down into invisible particles, those molecules will still be there, mixed into the sediments, creating a thin but distinct layer of artificial polymers unlike anything in the natural geological record. A geologist millions of years from now might extract sediment cores and analyze them molecularly. Most layers would show the usual organic compounds, natural polymers like lignin and cellulose, typical breakdown products of biological material. But then they'd hit one specific layer, maybe just a few centimeters thick, compressed from thousands of years of deposition, and in that layer they'd find something weird. Molecular structures that don't match anything biological. Long-chain hydrocarbons with unusual bonding patterns. The ghost of plastic. The molecular fossil of a civilization that invented synthetic materials. Would this signature survive 100 million years? Honestly, we don't know. Probably not intact. But even heavily degraded, even broken down and partially recycled through geological processes, it would likely leave some anomaly. Some chemical weirdness in that specific layer that doesn't match the layers above or below. Then we get to the really dramatic stuff. Radioactive isotopes. Our civilization has done something that has never happened before in Earth's history. We've created elements that don't exist naturally. When we detonate nuclear weapons or operate nuclear reactors, we produce isotopes like plutonium-239, cesium-137, and strontium-90. These isotopes didn't exist on Earth before 1945. They're entirely artificial, the product of neutron bombardment in reactors and bombs, and they're spreading everywhere. Nuclear weapons testing in the 1950s and 60s scattered these isotopes globally. They're in the atmosphere, in the ocean, in the soil. They're being absorbed by plants and animals, incorporated into bones and shells, locked into sediments as organisms die and sink to the ocean floor. Right now, all over the planet, layers of sediment are being deposited that contain radioactive isotopes that have never existed on Earth before. These isotopes decay over time, but their decay products are distinctive. Plutonium-239 has a half-life of 24,000 years, which means detectable amounts would persist for hundreds of thousands of years. Even after it decays completely, the ratio of its decay products, specific uranium and thorium isotopes, would be anomalous. They'd show up in exactly the proportions you'd expect from plutonium decay, not from natural processes. This is a smoking gun that would survive millions of years. Any civilization that developed nuclear technology would leave this signature. The specifics might vary, they might use different reactor designs or weapon types, but the basic principle holds. Split atoms, create artificial isotopes, scatter them globally, leave a permanent mark in the geological record. Scientists have already started calling our current era the Anthropocene, the age of humans, specifically because we're leaving such a dramatic mark on Earth's geology. Future geologists won't have to guess when human civilization existed. They'll see it in the rock record as clearly as we see the asteroid impact that killed the dinosaurs. A thin layer marking a geological instant when everything changed, when atmospheric chemistry shifted, when new isotopes appeared, when artificial molecules showed up in the sediments. But here's where it gets really interesting. If we're leaving such obvious signatures, wouldn't a previous industrial civilization have left similar ones? And if they did, would we recognize them? The answer depends on timing. Our chemical fingerprints will be obvious for thousands of years, probably detectable for millions. But 100 million years? 200 million? The signatures would be degraded, mixed, diluted by the slow churning of geological processes. They might still be there, but you'd have to know exactly what to look for, and exactly where to look for it. You'd need sediment cores from the right locations, places where continuous deposition occurred without disruption. You'd need incredibly precise chemical analysis, looking for subtle anomalies in isotope ratios that might be natural variation or might be something else. You'd need to analyze thousands of samples spanning millions of years, searching for that one thin layer where something weird happened. And even then, even if you found anomalies, how would you know they were artificial? How would you prove they came from industrial activity and not some unknown natural process? A carbon isotope spike could be a massive forest fire. A nitrogen anomaly could be some unusual algal bloom. Even radioactive isotopes could theoretically come from natural nuclear reactors, which have occurred on Earth before in uranium-rich deposits. This is the fundamental problem with looking for chemical fingerprints of ancient civilizations. The signatures exist, they're real, they're measurable, but they're subtle enough, ambiguous enough, that they could be explained away as natural variations. Unless you found multiple independent signatures all occurring in the same layer, all pointing to industrial activity, you'd never be certain. But uncertainty doesn't mean we shouldn't look. It just means we need to be smart about where we look and what we look for. We need to identify the most stable, most distinctive chemical signatures and search for them in the best preserved sediments from Earth's deep past. We need to establish what natural variation looks like, so we can recognize when something exceeds natural bounds. Because here's the thing, if another industrial civilization existed 200 million years ago and lasted just a few thousand years, we might have already seen their chemical fingerprints and dismissed them as anomalies, as measurement errors, as natural variations we don't fully understand. The evidence might be sitting in sediment cores right now, waiting for someone to ask the right questions. Or maybe it's not there. Maybe we're the first. Maybe industrial civilization is so rare, so unlikely, that it's only happened once in Earth's entire history. But we won't know until we look, really look, with the right tools, the right questions, and the willingness to consider possibilities that seem impossible. Because chemistry doesn't lie. Elements and isotopes follow rules that can't be broken. If someone changed Earth's chemistry millions of years ago, some trace of that change still exists, somewhere, in some layer of sediment, waiting. So now we need to ask a more pointed question. If we're looking for evidence of a civilization that existed millions of years before us, what exactly should we be looking for? And more importantly, does the geological record contain anything that makes us pause? Anything that doesn't quite fit the standard narrative? The answer is yes, not proof, understand. Not evidence of ancient alien cities or prehistoric nuclear wars, but anomalies, strange spikes and dips in the chemical composition of rocks, events that happened remarkably fast by geological standards, patterns that look disturbingly familiar when we compare them to what our own civilization is doing to the planet right now. Let's start with the big one, the event that actually inspired the Silurian hypothesis in the first place. 56 million years ago, something extraordinary happened to Earth's climate. We call it the Paleocene-Eocene Thermal Maximum, or PTM, and it's one of the most mysterious events in our planet's recent geological history. Here's what we know. Over a period that might have been as short as 5,000 years, which is nothing in geological time, someone or something released massive amounts of carbon into Earth's atmosphere. We're talking about 3,000 to 7,000 gigatons of carbon. For comparison, humans have released about 400 gigatons since the Industrial Revolution began. Whatever happened during the Petman was an order of magnitude larger. The effects were dramatic. Global temperatures shot up by 5 to 8 degrees Celsius. The oceans warmed. The chemistry of seawater changed so radically that huge numbers of deep-sea organisms went extinct. Acidification spread through marine ecosystems. Weather patterns shifted dramatically. Tropical conditions reached all the way to the Arctic Circle. Sound familiar? It should. Because what happened during the Petman looks remarkably similar to what we're doing to the planet right now. Same basic process. Massive carbon release, rapid warming, ocean acidification, ecosystem disruption. The PEPM is basically a preview of our own future if we don't change course. But here's the unsettling part. We don't actually know what caused it. The dominant theory is that massive volcanic activity in the North Atlantic released enormous amounts of carbon dioxide. Alternatively, warming oceans might have destabilized methane hydrates on the ocean floor, creating a runaway feedback loop. Both are plausible natural explanations. But when scientists first studied the PEPM in detail, they noticed something that made them uncomfortable. The rate of carbon release during the PEPM was almost identical to modern anthropogenic carbon emissions, not similar, nearly identical. The chemical signature in the rocks suggested a relatively sudden pulse of carbon, concentrated over a geologically brief time span. Now, nobody serious is suggesting the PEPM was caused by an ancient industrial civilization. The evidence doesn't support that. But it raises a fascinating question. If our civilization disappeared tomorrow, and geologists 56 million years in the future found the chemical signature of our industrial age, would they be able to distinguish it from a natural event like the PEPM? Or would it just look like another mysterious carbon spike, another unexplained anomaly in the long history of Earth's climate? This is the core insight of the Silurian hypothesis. Not that ancient civilizations definitely existed, but that their traces might be fundamentally indistinguishable from certain natural events if enough time has passed. But the PEPM isn't alone. The geological record is peppered with similar anomalies, strange chemical excursions that happened remarkably fast and then disappeared. Events that don't quite fit our models of natural planetary processes. Take the torsion oceanic anoxic event about 183 million years ago. Another massive carbon pulse, another episode of rapid warming and ocean acidification, another mass extinction in marine ecosystems. The pattern is eerily similar to the Piet, just pushed back further in time. Or consider the various isotope excursions throughout the Mesozoic and Paleozoic eras. Brief spikes in carbon-13 ratios, sudden shifts in oxygen isotopes, rapid changes in the chemical composition of ancient sediments. Most of these have natural explanations: volcanic activity, changes in ocean circulation, variations in biological productivity. But some remain puzzling. The timing is too fast, the magnitude too large, the pattern too complex to fit simple natural models. None of this is evidence of ancient civilizations. Let's be absolutely clear about that. These are natural events with natural causes, but they demonstrate something important. Earth's chemistry can change dramatically over relatively short timescales, and distinguishing between natural rapid changes and hypothetical artificial ones becomes nearly impossible once you're looking back tens of millions of years. Then there's the Cambrian explosion. About 541 million years ago, something extraordinary happened. For 3 billion years, life on Earth had been simple. Bacteria, algae, simple multicellular organisms, nothing you'd look at twice. Then suddenly, geologically speaking, everything changed. Over a period of perhaps 20 to 25 million years, which sounds long but is incredibly brief in evolutionary terms, nearly all the major animal body plans that exist today appeared in the fossil record. Eyes evolved, shells and skeletons developed, predation became sophisticated, complex ecosystems emerged seemingly out of nowhere. Darwin himself was troubled by the Cambrian explosion. It seemed too fast, too sudden to fit his model of gradual evolutionary change. Modern paleontologists have better explanations now. Rising oxygen levels, genetic regulatory systems reaching a threshold complexity, arms races between predators and prey, environmental changes creating new niches, all natural processes. But the Cambrian explosion demonstrates something crucial. Evolution can move incredibly fast when conditions are right. It can produce extraordinary complexity in timeframes that seem impossibly brief. And the further back we look, the more compressed these revolutionary changes appear. If intelligence had evolved before us, if some earlier species had developed technology and civilization, would we necessarily see it coming? Or would it appear to emerge suddenly from the fossil record, just like the Cambrian explosion appears to us? Intelligence itself leaves almost no fossil trace. Tools and technologies would vanish in geological time. We'd be left looking at before and after snapshots, wondering what happened in between. Then there are the mass extinctions, 5 major ones in the past 500 million years, plus numerous smaller events. Some we understand well. The asteroid impact 66 million years ago that killed the dinosaurs left a clear signature, a global layer of iridium-rich sediment, shocked quartz, tsunami deposits, the smoking gun pointing to a specific crater in Mexico. But others are more mysterious. The end Permian extinction 252 million years ago killed 96% of all marine species and 70% of terrestrial vertebrates. It's the closest life on Earth has ever come to complete annihilation. The cause? Probably massive volcanic eruptions in Siberia, releasing enormous amounts of carbon dioxide and sulfur dioxide. But the details remain debated. The extinction happened in multiple pulses. Some groups disappeared rapidly, others declined gradually. The pattern is complex, suggesting multiple, interacting causes. The late Devonian extinctions, a series of events between 375 and 359 million years ago, are even more puzzling. Marine life was devastated, particularly reef ecosystems and bottom-dwelling fish. But land plants and animals largely survived. The pattern doesn't fit a simple asteroid impact or volcanic catastrophe. Climate change probably played a role. Ocean anoxia certainly contributed. But the precise trigger remains elusive. What's interesting about these events from our perspective is how difficult they are to fully explain even with modern scientific tools. We can identify the approximate timing. We can measure chemical changes in the rocks. We can see which species disappeared and which survived. But reconstructing the exact chain of causation, the precise sequence of events that led to catastrophe, remains challenging even for extinctions that happened relatively recently. Now imagine trying to identify the signature of an industrial civilization in rocks 100 million years old. You wouldn't be looking for buildings or roads. Those would be gone, completely eroded and subducted. You'd be looking for chemical anomalies, spikes in carbon isotopes, changes in metal concentrations, patterns in sediment deposition. But these same signatures could be produced by volcanic activity, by shifts in ocean chemistry, by changes in biological productivity, by asteroid impacts. Distinguishing natural causes from hypothetical artificial ones would require incredibly detailed analysis. And the further back you look, the more degraded and ambiguous the evidence becomes. Consider plastic. We produce 400 million tons of it every year. It's accumulating in the oceans, breaking down into microplastics that are spreading throughout marine ecosystems. Surely plastic would leave a lasting signature, right? It's artificial, unnatural, clearly the product of industrial chemistry. But plastic is just long-chain hydrocarbons, complex organic molecules. Given enough time and enough heat and pressure, it breaks down. The carbon atoms get recycled into other compounds. Within a few million years, any plastic we've created will have decomposed completely. Future geologists might detect a brief spike in certain organic compounds in sediments from our era. But would they recognize it as artificial? Or would it just look like a natural variation in organic chemistry? The same applies to metals. We mine and refine enormous quantities of aluminum, copper, iron, rare earth elements. We concentrate them, shape them, distribute them across the planet. Surely that would leave a trace. It does, but not the kind you'd expect. Most refined metals oxidize and corrode relatively quickly once human maintenance stops. Within thousands of years, they've rusted or degraded back into mineral forms. Within millions of years, they've been redistributed by erosion and geological processes. You might find slight statistical anomalies in metal distribution patterns, concentrations that are a bit higher than expected in certain sedimentary layers. But distinguishing this from natural variation would be nearly impossible. The point isn't that these anomalies in Earth's history are evidence of prior civilizations. They almost certainly aren't. The pattern was probably volcanic activity. The Cambrian explosion was natural evolution responding to environmental opportunities. The mass extinctions had natural causes, even if we haven't pinned down every detail. But these events demonstrate how difficult it is to read Earth's deep history. How easily dramatic events can leave ambiguous traces. How natural and artificial processes can produce remarkably similar signatures once enough time has passed. They show us that absence of evidence isn't necessarily evidence of absence, especially when we're looking back across tens or hundreds of millions of years, and they give us a healthy dose of humility. We like to think our civilization is special, unprecedented, the pinnacle of Earth's history. But the planet is 4.5 billion years old. Complex life has existed for over 500 million years. Animals with sophisticated nervous systems have been around for more than 600 million years. That's an enormous amount of time. Vast stretches where something unexpected might have happened, and we'd have almost no way to detect it now. So when we look at these anomalies, these mysterious spikes and extinctions and explosions of complexity, we're not seeing proof of ancient civilizations, but we are seeing the limitations of our knowledge, the gaps in the geological record, the places where our understanding becomes fuzzy and our certainty evaporates. And that, perhaps, is the most unsettling realization of all. Not that ancient civilizations definitely existed, but that if they had, we might never know. The Earth keeps secrets very, very well. So if we accept that industrial civilizations might vanish from the geological record within a few million years, the next question becomes unavoidable. Who could have done it? What species, living when, might have built cities, developed technologies, and then disappeared so completely that we'd never know? The answer is both stranger and more scientifically grounded than you might expect. Let's start with the most famous candidate, one that's captured imaginations since scientists first seriously considered the question: intelligent dinosaurs. Now, before you dismiss this as science fiction, consider the facts. Dinosaurs dominated Earth for 165 million years. That's not a typo. 165 million years. For context, primates have only existed for about 65 million years. Humans have been around for roughly 300,000 years. Dinosaurs had time, absurd amounts of time. Time for evolution to experiment, to refine, to produce outcomes we can barely imagine. And here's what paleontologists realized in the 1970s and 80s. Some dinosaurs were getting seriously intelligent. The most famous example is Troodon, a small theropod that lived during the late Cretaceous, about 75 million years ago. Troodon had one of the highest brain-to-body ratios of any dinosaur. Large, forward-facing eyes suggesting binocular vision and depth perception. Grasping hands with opposable digits, evidence of complex social behavior and possibly cooperative hunting. Paleontologist Dale Russell from the Canadian Museum of Nature looked at Troodon's anatomy and asked a simple question. What if the asteroid hadn't hit? What if dinosaurs had kept evolving for another 65 million years? He created what he called the dinosauroid, a speculative reconstruction of what an intelligent, technologically capable descendant of Troodon might have looked like. The result was startling. A bipedal creature standing upright, with large eyes, reduced snout, grasping hands with 3 digits. It looked eerily humanoid, not because Russell was imagining little green dinosaur people, but because the requirements for technological civilization seemed to drive evolution towards similar solutions. You need hands, or something like them, appendages capable of precise manipulation. You need binocular vision to coordinate complex tasks. You need a large brain relative to body size. You need social structures capable of knowledge transfer across generations. Troodon was evolving toward all of these things, not because it was trying to become human, but because intelligence and tool use create specific evolutionary pressures that tend to produce similar anatomical solutions. Now, could Troodon or its descendants have actually built a civilization? The standard objection is immediate. Dinosaurs didn't have fire. And without fire, you can't smelt metals, can't develop advanced chemistry, can't create the technological foundation for industrial civilization. But here's where it gets interesting. Dinosaurs didn't have fire because they never needed fire. They were already warm-blooded or partially warm-blooded. Many species lived in climates that never got cold enough to require external heat sources, and they were eating raw food just fine. Fire is a human solution to human problems. A hypothetical dinosaur civilization might have followed completely different technological pathways. Maybe they developed advanced bioengineering instead of metallurgy. Maybe they built structures from modified plant materials or ceramics that could be shaped without high temperatures. Maybe their technology was so different from ours that we literally wouldn't recognize it as technology if we found it. Consider this. If you showed medieval Europeans a microchip, they wouldn't recognize it as technology. It would look like a piece of decorated pottery or maybe jewelry. Now imagine trying to recognize technology developed by a species with different sensory systems, different cognitive architecture, different evolutionary pressures than humans. Would we even know what we were looking at? But let's be honest. The asteroid probably prevented any chance of dinosaur civilization. 66 million years ago, a rock 6 miles wide slammed into what's now the Yucatan Peninsula with a force of 10 billion atomic bombs. The impact winter that followed wiped out roughly 75% of all species on Earth. If any dinosaur species had been approaching intelligence, they died with the rest. But dinosaurs aren't the only candidates, not even close. Let's talk about something alive right now. Something that's been evolving intelligence along a completely independent pathway from vertebrates, cephalopods, octopuses, squid, cuttlefish. These animals are absurdly intelligent. Octopuses can solve complex puzzles, use tools, recognize individual humans, and even display what looks like playful behavior. They have distributed nervous systems with neurons throughout their bodies, not just in their brains. Each arm has its own neural cluster capable of independent decision-making. It's an alien form of intelligence, evolved from the ground up along completely different principles than vertebrate brains. And they've had time. Cephalopods emerged around 500 million years ago during the Cambrian explosion. They've been around nearly twice as long as dinosaurs. For 500 million years, evolution has been experimenting with cephalopod body plans and nervous systems. But here's their problem. The reason we probably don't have to worry about ancient octopus civilizations, they're almost entirely marine. And marine environments make developing technology incredibly difficult. You can't create fire underwater. Most chemical reactions that require heat are impossible. Metallurgy, ceramics, even basic controlled combustion, all require air. More fundamentally, water is so effective at meeting basic needs that there's less evolutionary pressure to develop technology. You don't need clothes. You don't need shelter from weather in the same way terrestrial animals do. Food is everywhere. Why would you develop agriculture when you're surrounded by edible organisms? Some researchers have suggested that truly advanced marine civilizations might be possible, but they'd have to develop through completely different technological pathways than terrestrial civilizations. Maybe they'd master genetic engineering of marine organisms long before they developed anything we'd recognize as machines. Maybe they'd build with coral and living structures instead of stone and metal. Maybe their entire civilization would be biological, their technology indistinguishable from ecology. If such a civilization had existed, say, 300 million years ago during the Carboniferous, when oxygen levels were high and life was explosively diverse, how would we know? Their structures would have been consumed by marine organisms within decades of abandonment. Their genetic engineering might have looked like normal evolution if we found the fossils. Their knowledge would have been stored in forms that degraded instantly after death. They could have built cities that covered the ocean floor, developed mathematics and philosophy, even sent expeditions onto land in protective vessels. And 300 million years later, we'd have absolutely no way to detect them. But let's push further into strangeness. What about intelligence in forms we'd barely recognize as life? Evolution has produced intelligence independently at least 3 times that we know of. Vertebrates, cephalopods, and insects. Possibly more if you count things like slime molds that show problem-solving abilities despite having no nervous system at all. This tells us something crucial. Intelligence isn't some unique miracle that happened once to primates. It's a solution that evolution finds again and again when the right conditions exist. And those conditions are pretty straightforward. Complex environment requiring navigation and decision-making. Social interactions that reward prediction and communication. Survival challenges that favor learning and memory over pure instinct. These conditions have existed throughout Earth's history. During the Devonian 400 million years ago, when armored fish dominated the seas. During the Carboniferous, when giant arthropods ruled the land. During the Permian, before the greatest mass extinction in Earth's history wiped out 96% of all species. Any of these periods could have produced intelligent lineages, species that developed tool use, communication, eventually technology, and then vanished, either in one of the 5 great mass extinctions or simply by evolving into something else, going extinct naturally, the way 99.9% of all species eventually do. The evolutionary requirements for technological civilization seem to be fairly specific, but not impossibly rare. You need some form of manipulative appendages, not necessarily hands, but something capable of precise manipulation. You need sensory systems that can perceive the world in enough detail to model it mentally. You need a large enough brain or information processing system to support abstract reasoning. You need social structures capable of knowledge accumulation and transfer. These requirements have been met multiple times in Earth's history. Dinosaurs came close. Cephalopods came close in a different direction. Early mammals during the age of dinosaurs were developing increasingly sophisticated brains and manipulative abilities. What if one of these lineages crossed the threshold? What if, 300 million years ago, a species of social, tool-using, fire-making reptiliomorph developed the cognitive capacity for symbolic reasoning? What if they spent 50,000 years, maybe 100,000 years, building a civilization around the supercontinent Pangaea? They'd have left almost nothing. A few weird chemical ratios in 300 million-year-old rocks. Maybe some unusually shaped stones that could be tools or could be geological formations. Perhaps some peculiar patterns in the fossil record that could indicate extinctions from habitat destruction, or could just be normal background extinction. We'd never know for certain, and that's the point. The geological record is like a book where 99.9% of the pages have been torn out, and most of the remaining pages have been water-damaged, burned, or eaten by insects. We're trying to reconstruct the entire story from the occasional legible paragraphs scattered across billions of years. Could we be missing civilizations in those gaps? Not just one, but many. Could Earth's history include multiple rises and falls of intelligence, each one thinking they were the first, the special ones, the only conscious beings to ever contemplate their own existence? The honest scientific answer is, we don't know. We probably can't know. The evidence would be too subtle, too degraded, too easily explained by natural processes. But the possibility is real, and that possibility changes how we think about intelligence, civilization, and our place in the vast story of life on Earth. We might not be the first. We're probably not even the most interesting. We're just the only ones asking the question right now. The only ones currently capable of wondering whether anyone asked it before. And somewhere, buried in rocks hundreds of millions of years old, there might be answers we'll never be able to read. Now zoom out. Not just from Earth, not just from human history, but from the galaxy. For a moment, forget deserts turning to grasslands, forget Neanderthals and Denisovans. Picture instead the Milky Way as it really is. A vast rotating disk of stars, hundreds of billions of suns, each with its own system of planets. Many of those planets are older than Earth. Some have been stable for billions of years. Some orbit stars longer lived and calmer than our own. If intelligent life can arise here, on a world that almost killed us before we began, why not there? This is the heart of what physicists call the Fermi paradox. Given the age of the galaxy and the sheer number of planets, intelligent life should not be rare. Civilizations should have had plenty of time to evolve, build technologies, explore space, maybe even spread from star to star. So where are they? We don't see star systems covered in solar collectors. We don't see artificial beacons sweeping the skies. Our radio telescopes pick up pulsars, quasars, and the hiss of the cosmic background, but not the chatter of galactic neighbours. The silence is strange. One way scientists try to explain this silence is with an unsettling idea called the Great Filter. The Great Filter is the notion that somewhere along the path from dead rock to galaxy-spanning civilization, there is a step that is incredibly hard to pass, a barrier that almost all life fails to cross, a filter that lets through only the rarest of worlds, the rarest of species. You can think of the history of life as a staircase. First step, simple chemistry, then self-replicating molecules, then single-celled life, then complex cells with nuclei, multicellular organisms, intelligence, technology, long-lived stable civilizations, and finally, maybe interstellar expansion. The Great Filter is somewhere on that staircase, but we don't know where. Maybe the filter is at the beginning. Maybe the jump from simple molecules to self-replicating life is almost impossibly rare. In that case, we might already have passed it. Our existence would be the cosmic lottery ticket, the proof that we are one of the few. Or maybe the filter lies ahead. Maybe the truly difficult step is not inventing technology, but surviving it. Not discovering fire, but learning not to burn the world down. If the Great Filter is in our future, it would explain the silence. Civilizations might arise on many worlds, build cities, invent radios, maybe even briefly look out at the stars, and then they disappear, over and over again. A galaxy full of beginnings, almost none of them lasting long enough to become visible across light years. This is where the Silurian hypothesis slips quietly back into the frame. Because if there is a great filter, if civilizations usually destroy themselves or collapse before they spread beyond their home worlds, then Earth would not be an exception. We might not be the first minds to wonder about the stars from this planet. We might just be the first whose traces we can still see. Imagine again that earlier civilization, deep in Earth's past. Not reptiles in sci-fi suits. Not necessarily anything like us at all. It could have been a species of cephalopods in an ancient shallow sea, or social insects on some long-vanished supercontinent, or something stranger, something that thought with a very different brain but still made tools, stored knowledge, altered its environment. If they reached a technological phase, they would have faced the same basic constraints we do: finite resources, a fragile climate, ecosystems balanced on thin margins, the physics of energy and entropy that never change, no matter what shape your hands have or how you count numbers. Consider what advanced civilizations attempted to do. They mine, they burn, they dig up concentrated pockets of energy, coal, oil, gas, uranium, and spread their byproducts through air and water and soil. They dam rivers, clear forests, rearrange coastlines. They build networks that depend on fragile global interconnections. They create technologies whose full consequences they only dimly understand. Each of these moves brings benefits in the short term: more energy, more food, more comfort, more information. But each also loads the environment with delayed consequences: temperature rising a fraction of a degree at a time, oceans acidifying molecule by molecule, topsoil thinning harvest by harvest, species disappearing one unnoticed population at a time. You don't need to imagine any malice for things to go badly wrong. All you need is short-term thinking amplified by powerful tools. On Earth today, we can list our own potential filters: runaway climate change that destabilizes agriculture and turns bread baskets into deserts. Ocean collapse as food chains unravel from the bottom up. Pandemics amplified by dense global populations. Nuclear war or other weapons we haven't yet invented. Advanced AI systems that reshape economies and institutions faster than we can adapt. Resource depletion that triggers cascading political and social breakdowns. Any one of these might not wipe out every last human, but they could collapse the complex, energy-intensive civilization we rely on. They could take us back from global networks and orbital satellites to scattered, struggling survivors wondering what went wrong. Now rewind the tape of Earth's history. Could something like this have happened before? A prior civilization might have discovered powerful energy sources that left chemical fingerprints we mistake for natural events. A spike in greenhouse gases, sudden releases of carbon from deep underground, rapid warming followed by mass extinctions. To we who come later, it would look like volcanism, like methane clathrate release, like one of the many natural catastrophes that dot the geological record. Maybe that's all it was. Or maybe some of those abrupt transitions, the ones that look unnervingly like our own current trajectory, were the signatures of someone else's great filter. Picture them at their peak. Cities, whatever city meant for them, thriving, information flowing, tools becoming more subtle, more powerful, a sense that progress is inevitable, that tomorrow will be richer and more comfortable than today, debates about the future, about ethics, about what kind of world they want to build for their descendants. They begin to understand the risks. Some call for caution, others say the fears are overblown, that technology will solve the problems it creates. There are attempts at regulation, compromises, half measures, and then a tipping point, a summer that never ends, a winter that refuses to arrive, harvests that fail just a little too often in just a few too many places. Supply chains, that invisible nervous system of any civilization, begin to fray. If they had global trade, it starts to seize up. If they had complex governance, it begins to splinter under the strain. If they had weapons capable of devastation, the temptation to use them grows. From that point, collapse might be fast. A few decades, a human lifetime. Not long at all in geological terms. Cities are abandoned. Knowledge is lost, not all at once, but piece by piece. Critical technologies fail, as key components can no longer be manufactured. Populations fall. Memories turn into myths, then vanish entirely as the last people who remember those days die. Rain washes through the empty streets. Wind carries dust over silent machines. Within a few thousand years, most of their structures are gone. Within a few million, almost every trace is erased or buried deep, scattered and mixed with the detritus of natural processes. If they had satellites, they would have deorbited and burned in the air. If they had plastics, they might linger as microfragments in ancient sediments, indistinguishable from the breakdown products of ancient algae. If they had metal, it would corrode, melt, be subducted into the mantle and recycled as magma. From our vantage point, hundreds of millions of years later, we would see only a blip, a strange chemical anomaly, a rapid extinction, a thin line of disturbed rock, another mystery in a planet full of mysteries. This is what the great filter looks like from the inside. Ordinary decisions made by ordinary beings, playing out over generations, until the world they depend on shifts beneath their feet. If the Silurian hypothesis were true, if there had been one or many technological civilizations before us that rose, flourished, and fell, it would tell us something sobering about the path we are on. It would mean that intelligence is not enough. Tool-making is not enough. Complex social systems, trade networks, language, even science. None of these guarantee long-term survival. Surviving the great filter, if it lies ahead, would require something more elusive. The ability to restrain ourselves, even when we have the power not to. The patience to think in centuries instead of election cycles or quarterly profits. The wisdom to see the planet not as a warehouse of resources, but as a delicately balanced system we are part of, not masters of. It would mean that the real test of civilization is not how fast it grows, how high its towers reach, or how bright its cities shine from orbit. The real test is how gently it can learn to live on its world, after the first wild burst of technological adolescence. If there were others before us, they might have stood at this same crossroads. They might have glimpsed the danger, debated it, argued about models and predictions. Some of them might have begged their societies to slow down, to change course, to leave fossil carbon in the ground, to rethink their tools. Maybe they didn't. Maybe they couldn't. Maybe the pressures of competition, fear, and short-term gain were too strong. Their failure, if it happened, would be our warning. Because for us, the Silurian hypothesis isn't just a speculative game about ancient lizard scientists or forgotten insect empires. It's a mirror held up to our own moment, a reminder that if the universe is quiet, it may be because the path we are walking is much more fragile than it appears. Lying in the dark, listening to these possibilities, you can feel the scale of it all. Billions of years behind us. Billions, perhaps, ahead. An unknown number of worlds where life might have flickered and gone out without ever touching the stars. And here we are, on a small temperamental planet that has nearly ended us once already, building a civilization that could, if we're not careful, become just another thin, ambiguous line in the rocks for some future mind to puzzle over. If prior civilizations existed and fell, their most important legacy wouldn't be their technology or their monuments. It would be the lesson written in their absence. That intelligence without foresight is a phase, not a destiny. That power without restraint is just another name for self-destruction. That the real measure of a civilization is how long it can keep the lights on without burning down its only home. As you drift towards sleep, you can hold that thought lightly. Maybe we're alone. Maybe we're the first. Maybe we're one in a long hidden chain of civilizations that rose and vanished on this same blue world. We may never know, but the silence of the stars, the mysteries in the rocks, and the fragility of our own systems all whisper the same quiet suggestion. Whatever happened here before, if anything did, let's try to make sure we're not just another forgotten experiment, another failed attempt to pass the great filter on a planet that will keep turning long after we're gone. So why does any of this matter? Why spend time imagining lost civilizations, vanished in deep time, societies erased so thoroughly that not a single city, not a single tool, not a single inscription survives? Because this isn't just a story about us. It's a dress rehearsal for how we look for anyone else. If it's this hard to find traces of our own industrial civilization after just a few 100,000 or a few million years, what does that say about trying to detect civilizations on other worlds, buried under billions of years of geology? The Silurian hypothesis wasn't invented just to ask, what if we're not the first? It was also invented to ask, what would it even look like if we weren't? What would be left? What would show up in the rocks, the chemicals, the climate record? And once you ask that about Earth, you can't help but ask it about Mars, about Venus, about planets orbiting distant stars that we'll never visit, only observe as tiny points of light. Think about Mars for a moment. We look at its surface today and see a cold, dry desert. Rusted rocks, thin air, dust, maybe a few patches of seasonal frost. But rewind the clock a few billion years and the story changes. Ancient river valleys, lake beds, maybe even a northern ocean. A world with thick air, liquid water, a climate that, at least for a while, could have supported life. If a Martian civilization had risen and fallen back then, long before our planet cooled enough for complex life, what would we see now? We probably wouldn't see skyscrapers or roads. Wind and dust storms would grind exposed structures into sand in a few million years. Temperature swings would crack and shatter anything left on the surface. Meteor impacts would churn the crust. Just like on Earth, the visible, recognizable artifacts would vanish quickly on geological timescales. But chemical fingerprints, those might last. If an industrial civilization had burned fossil carbon, you might see strange spikes and dips in ancient Martian sediments. Sudden shifts in carbon isotope ratios, the same way our own fossil fuel use is imprinting a signal today. If they used chlorine-based industrial processes, you might see weird concentrations of chlorinated compounds. If they mined metals, you might see unusual distributions of nickel, copper, or rare earth elements in old lake deposits. From orbit, we can already see layers of rock on Mars stacked like pages in a book. Dark bands, light bands, repeating cycles, each one a snapshot of ancient climate. Freeze and thaw, wet and dry, calm and storm. For now, we read those layers mostly as natural history. But the Silurian hypothesis asks, what if some of those pages contain more than just weather? Not proof, just anomalies, chapters that don't quite fit the pattern. That's where future research comes in. As we get better at exploring other planets, the question quietly shifts from, is there life, to is there a story? Not just microbes existing, but worlds that changed. Worlds that may have had their own brief experiments with complexity, with technology, with something like us, and then lost it. To detect that, we need a checklist, markers to look for. On Mars, that means seeking out ancient lake beds and ocean floors, just like we do on Earth. Places where fine sediments settled slowly over time, layer by layer, trapping chemical information like a tape recorder. It means sending rovers, and eventually people, to drill deep into those sediments, not just scraping the surface dust. We'd look for sudden, sharp changes in carbon and oxygen isotopes, suggesting rapid climate shifts not easily explained by volcanoes or orbital cycles. Unusual concentrations of metals that tend to be associated with industrial activity on Earth, things that don't match natural weathering patterns. persistent layers of synthetic-looking molecules, long-lived fluorinated or chlorinated compounds that, on Earth, we mostly create in factories. Right now, our robots on Mars are like hikers walking across the cover of a book, skimming a few lines on the first page. Future missions will have to be more like geologists and librarians, cataloguing, drilling, reading deeply. And Mars is the easy case. Exoplanets are harder. Most of the worlds we know orbit distant stars, so far away that they're just single pixels of light, even in our best telescopes. We can't see their landscapes, we can't read their rocks. All we get is the faint signature of their atmospheres, passing in front of their stars, shaving off tiny bits of starlight in specific colours. But even that is enough to start asking Silurian-style questions. If we stare at a distant planet and see oxygen and methane coexisting in its atmosphere, that's already strange. Those gases react with each other. They don't stay balanced for long without something replenishing them. Life is one explanation. But what about more specific, more puzzling signals? Imagine detecting a thick layer of chlorofluorocarbons, CFCs, in an exoplanet's air. On Earth, these are synthetic industrial chemicals invented in the 20th century, used in refrigeration and aerosols, and almost entirely phased out when we realized they were tearing a hole in the ozone layer. They don't occur in high concentrations naturally. They're pure artifacts. If you saw that on a distant world, you'd be looking at a Silurian problem, a planetary-scale signal that says something here was manipulating its environment, not just microbes, not just forests, something making molecules that don't arise by accident. Or think of a planet with a wildly out-of-balance carbon cycle, a strong greenhouse effect that switched on very quickly, accompanied by an unusual isotope signature, then a sudden crash, a spike, and then a silence. It might be a giant volcanic event, a comet impact, or it might be something more like our Anthropocene, a brief industrial flare visible across interstellar distances, a planet that heated itself, changed its air, maybe lost its ice, and then either stabilized or didn't. The Silurian hypothesis trains us to see those planetary stories not as neat, smooth lines, but as jagged, interrupted ones. Long stretches of quiet, and then brief, sharp bursts of complexity that might, if we're looking carefully enough, stand out in the data. Back on Earth, the same thinking guides where we look for our own deep history. We tend to think we know our planet well. We've mapped the continents, we fly over the oceans, we drill for oil and gas. But in geological terms, our sampling is incredibly thin and incredibly biased. Most of what we know comes from rocks that happen to be exposed at the surface today. Cliff faces, road cuts, quarries, canyon walls, a random, patchy mosaic of time. Huge stretches of Earth's history are buried miles deep or have been subducted back into the mantle, recycled by plate tectonics. If a civilization had risen 100 million years ago and built its cities on land, most of those land surfaces no longer exist. They've been scraped away by erosion or shoved under. Continents. The pages have been ripped out of the book and burned. But there is one archive that's more complete, one place where the pages are still stacked in order, mostly untouched, the ocean floor. When tiny particles settle out of seawater, they drift down through the dark and land on the seafloor like slow, endless snow. Bits of plankton shells, volcanic ash, dust blown from deserts, microscopic fragments of rock, layer after layer, year after year, millions of years. In the deepest parts of the oceans, those layers build up slowly but steadily, preserving an almost continuous record. If you want to look for subtle signs of something unusual, chemical anomalies, strange isotopes, metal concentrations, the deep ocean sediments are the best place we have, but they're also the hardest to get to. We've mapped the surfaces of Mars and the Moon in more detail than the floor of our own oceans. Drilling into those ancient sediments requires ships, specialized rigs, and international collaborations. Most of the cores we've taken only scratch the last few tens of millions of years. The deeper, older layers remain mostly untouched, still waiting in the darkness. Future research inspired by the Silurian hypothesis would mean changing that, systematically sampling older and deeper oceanic sediments. Looking not for specific artifacts, but for oddities in the chemical record. Layers that say, something happened here that doesn't match our current models of volcanism, impacts, or natural climate cycles. We might find nothing except a better understanding of natural processes, or we might find puzzles, thin bands rich in certain metals, sudden global spikes in synthetic-like organics, signals that force us to ask new questions, design new experiments, refine our tools. Either outcome is valuable, because the real power of the Silurian hypothesis isn't that it proves or disproves ancient civilizations, it's that it sharpens our awareness of our own. When we look at Earth as if we were aliens, studying it 100 million years from now, we notice things we usually ignore. The way our carbon emissions will leave a sharp, narrow signature in the rock record, a black line of sudden warming and acidification. The way our plastics, if they survive in any form, might show up as tiny fragments in marine sediments, a strange layer of polymer-rich sand. The way our nitrogen fertilizers are already altering the isotope ratios in soils and rivers. We see our time for what it is, a brief, intense, geologically sudden experiment in planetary modification. From that perspective, questions of impact take on a new texture. It's not just, will we cause climate change? We already have. It's, what kind of layer do we want to leave? A mass extinction horizon, like the line that marks the end of the dinosaurs? A sudden spike of metals and pollutants that tells a story of a civilization that burned bright and crashed hard? Or a gentler, more ambiguous mark, a sign that we learned to shift from extraction to stewardship before the experiment ended? Future research driven by the Silurian hypothesis pushes us in two directions at once. Outward, toward the stars, designing telescopes and instruments not just to find water and oxygen, but to notice weirdness, chemical imbalances, industrial fingerprints, atmospheric stories, and inward, down into our own planet's memory, into sediments, ice cores, and ancient rocks, reading Earth's biography more carefully, looking for places where our assumptions break down, where the story's more complicated than we thought. It's a quiet kind of science. No dramatic revelations, no ancient city uncovered intact, just slow, patient accumulation of clues, better models, deeper cores, sharper instruments, a steady refinement of the question, how would you know if you weren't alone in the history of your own world? As you drift towards sleep, imagine future scientists floating above a distant planet, or aboard quiet ships over the midnight zone of our own oceans, lowering drills into black water, pulling up mud that hasn't seen light in tens of millions of years. Layer by layer they peel back time, they read the chemistry, they look for patterns, they test the hypothesis that civilizations, even if they're brief and fragile, can still leave whispers in stone and ice and dust. Maybe they find us. Maybe they find only nature. Either way, the search itself changes how we see our place in time. Because once you start asking what would remain of us in 1,000,000 years, or 100 million, or 1 billion, it becomes impossible not to feel the weight and the strangeness of existing right now, at the very beginning of that story, while the record is still being written. So what does it actually mean if we're not the first? Not just as a fun idea to think about in the dark before sleep, but as something we let all the way in. Past the curiosity, past the what if, down into that quiet place where we keep our sense of who we are. If we're not the first technological civilization on this planet, then everything changes, and at the same time, nothing changes at all. Because on one level, our stories about being special have always been fragile. We used to think the Earth was the center of the universe. Then we learned it wasn't. We used to think our continent, our nation, our tribe was the center of history. Then we learned history was bigger than any of us. We used to think our species had always been here. Then we found fossils that whispered otherwise. The Silurian hypothesis just pushes this one step further. Maybe our civilization, our cities, our satellites, our digital memories, are not the first time matter on this planet has organized itself into something that can think about the stars. Maybe we're just the latest verse in a very long song. At first, that can feel like a loss. If we're not the first, are we still important? If we're not unique, are we still meaningful? But step back, breathe. Notice what that feeling is made of. It's the same reflex that made our ancestors put the Earth in the center of everything. The same quiet insistence that says, for my story to matter, it has to be the only one. Deep time gently disagrees. From the perspective of hundreds of millions of years, no single civilization can ever be the whole story. Not ours. Not any imagined Silurian engineers building cities among carboniferous swamps. Not any future beings trying to decipher the strange chemistry of a long-vanished Anthropocene. Deep time humbles us. It also frees us. Because if you're not the first and you won't be the last, then you don't have to carry the weight of all meaning on your shoulders. You're a chapter, not the book. A verse, not the song. And chapters can be beautiful precisely because they end. Think again about those 1,280 bottleneck survivors from earlier in the story. They weren't the first humans. They weren't the last. Most of their names, their fears, their joys are gone forever. But the fact that you exist tonight, listening to this, means their lives mattered in a way they could never have understood. Their fingerprints are on your hands. Their decisions are in your DNA. Their persistence echoes in every breath you take. Now imagine a civilization before them, or parallel to them, or long, long before anything we would recognize as human. Imagine they had their own near bottlenecks, their own desperate games of survival against droughts and floods and volcanic winters, their own fragile networks of cooperation and trade, their own languages filling the air with meaning that has long since evaporated. To them, their world would have felt as immediate and permanent as ours feels to us. They would have worried about their children, argued about resources, celebrated small triumphs that no one remembers, stood under the same moon and wondered what it was. And then, they were gone. If the Silurian hypothesis is right, the traces they left behind would be almost invisible, a thin chemical fingerprint in a sediment layer, a slightly abnormal spike in certain isotopes, maybe a handful of puzzling fossils we haven't dug up yet. When the next intelligent species arrived, hundreds of millions of years later, they would find only whispers. This is where the humbling realization lands. From the outside, from the view of deep time, our skyscrapers and data centers and highways might be just another whisper, another faint layer, another brief rearrangement of atoms on a cooling planet. But from the inside, from our side of the glass, this moment is everything. You and I exist in this unbelievably thin slice of time when the planet is habitable. Your brain is awake, and a technological civilization is humming all around you. Billions of years before us, there was no one here to ask questions. Billions of years after us, there may be no one left to remember the answers. We live in a rare window when the universe is not just existing, but noticing itself. That doesn't make us less significant. It makes us a miracle among miracles. And it quietly raises a question. If we might not be the first, what kind of ancestors do we want to be? because whether or not a prior civilization existed, we are absolutely leaving a legacy for whatever comes next. If not for another species like us, then for the planet itself, for the rocks, the oceans, the atmosphere that will bear our chemical fingerprints for millions of years. We're writing in the language of geology now. We're changing the carbon balance of the air, redistributing metals from deep underground to a thin, rapidly corroding layer on the surface, scattering plastics into the sediments of riverbeds and sea floors. Even if all our buildings fell tomorrow, those signatures would linger. So imagine, 50 million years from now, some new intelligence studying the rocks the way we study ancient cliffs. Maybe they're descended from birds, or octopuses, or something we can't even picture. They drill a core sample, they scan the layers, and there it is, a sharp spike of carbon, strange plastics, unusual isotopes from nuclear reactions, a thin smear of fossils from a mass extinction event tied exactly to that chemical anomaly. They look at that layer and whisper whatever word they use for us. What do we want that word to mean? Does it mean catastrophe, wreckage, the ones who burned through everything and left the planet crippled? Or does it mean something more complicated? Maybe something like the first attempt. The civilization that almost destroyed itself, then changed course. The people who learned, just in time, that being smart also meant being responsible. Because this is the other side of the Silurian hypothesis. If we are not the first, then intelligence may not be a once-in-a-universe accident. It may be something planets do given enough time, like a forest sprouting after a fire, like coral reefs rebuilding after a storm. That sounds comforting. But it also suggests something sobering. If intelligence can arise more than once on the same world, it might also be fragile in the same ways, over and over. Easy to ignite, easy to extinguish. Maybe there's a pattern on worlds like ours. Life begins, it diversifies, it experiments with complexity. Every so often, a branch of that great tree manages to build cities, harness energy, alter the planet on a global scale. Some burn out fast, victims of their own success. Some last longer, learn to live within the limits of their world. Some vanish so completely that only a careful geologist eons later could guess they ever existed. Cycles of creation and destruction. Civilizations rising and falling like tides against the shore of deep time. We might be in the middle of one of those cycles right now. Our technology lets us see asteroids before they hit us, but also lets us change the climate faster than almost any natural process. We can cure diseases that once killed millions, but we can also build weapons that could end human history in an afternoon. We can listen to the heartbeat of distant galaxies, but we still struggle to cooperate with the people across our own borders. The Silurian hypothesis quietly asks, how many times has a planet like this reached this kind of moment? How many times has a thinking species stood at this crossroads with the power to protect its world, or to trigger its own erasure from the fossil record? If we are one more turn of that wheel, then responsibility comes bundled with wonder, because now we know, at least in principle, that our actions don't just affect our children, or their children. They might shape the conditions for life on this planet for millions of years. They might determine whether a future civilization, digging through ancient rocks, finds a mass extinction where we once stood, or a gentler transition into a stable, long-lived Anthropocene. In that sense, we are doing for the future what those 1,280 survivors did for us. They didn't know they were holding open the door for Homo sapiens, Neanderthals, Denisovans, and everyone who would come after. They were just trying to get through the next winter, the next drought, the next birth. Yet every small success, every child who lived instead of dying, was a vote cast in favour of a future they could never imagine. We're casting votes too. Every policy we pass or ignore, every forest we protect or cut, every technology we unleash or restrain, all of it is writing possibilities into the deep future. Maybe that's the real philosophical shock of the Silurian hypothesis. Not that we might not be first, but that we might be part of a lineage of minds, a chain of civilizations that never meet each other, but still pass something along, not in stories or artifacts, but in the state of the planet itself. A slightly richer atmosphere here, a slightly poorer biodiversity there, a climate nudged warmer or cooler, a biosphere that recovers in one particular way rather than another. Each civilization may vanish, but the world they leave behind becomes the starting point for the next experiment. You're living inside one of those experiments right now, and yet, for all our questions, there is a peace in not knowing. We may never find a definitive trace of a prior industrial civilization. The rocks might keep their secrets. The sediments might stay stubbornly ambiguous. Perhaps the only evidence that ever existed has already been subducted into the mantle, melted, and reborn as new crust. Some questions are like that. They're not puzzles to be solved, but horizons to walk toward. The Silurian hypothesis may always remain more parable than proof, a mirror we hold up to ourselves to see our own fragility, our own power, our own place in time, and that's okay. You don't have to know whether there were cities under the Permian sun to feel awe at the fact that there are cities under this one. You don't have to prove that other minds once walked this earth to recognize the quiet miracle that you are a mind on this earth now, breathing, listening, wondering. When you look at the night sky, you're seeing deep time in both directions. Light from distant stars, millions of years old, entering the eyes of a creature whose ancestors almost didn't make it through a bottleneck 900,000 years ago, living on a planet that might once have known other dreamers entirely. Maybe we are the first. Maybe we are not. Either way, we are part of a story so vast that no single species, no single civilization can ever own it. The Earth was here before us. It will be here after us. And somewhere in that long arc there is this small, shimmering interval in which we exist. We build, we destroy, we learn, we forget. We leave traces in stone and air and story. And then, like every civilization before us, and everyone that may come after, we pass the torch to whatever the planet will be next. You're a flicker in that long sequence. Brief, yes, but also irreplaceable, because no one else, in all the history of this world, has ever occupied this exact moment, with your exact memories, your exact questions, your exact capacity for wonder. Whether or not we are the first, we are here. And for now, in this quiet space between the beginning and the end, that is more than enough. So now, lying here at the very end of this journey, you can let the big idea settle in. The Silurian hypothesis isn't really about lizard people or secret ancient empires. It's about a question, a quiet, unsettling, strangely comforting question. If a civilization like ours had risen hundreds of millions of years ago, would we even know? We've seen how unlikely it is, how fragile the evidence really is. Most of Earth's surface gets recycled. Oceans open and close, mountains rise and erode away, cities, satellites, the entire industrial age. In a few million years, almost all of it would be gone. No skyscrapers, no smartphones, no internet cables, just a few chemical scars in the rocks, a thin layer of strange isotopes, odd spikes of carbon, plastic fragments ground into dust, molecules that don't quite fit the usual pattern of nature. If someone came after us tens of millions of years from now, they wouldn't find New York or Tokyo. They'd find anomalies, hints, questions, exactly what we find when we look back. That's the heart of the Silurian hypothesis. Not that there was a civilization before us, but that Earth's memory is short and deep time is long. The further back you go, the more the record blurs. Fossils become rare. Rocks are folded, melted, erased. Entire worlds of forests, oceans, climates, and creatures come and go with barely a trace. So we ask, could a technological species have flickered across the surface, changed the planet for a geological heartbeat, and vanished, leaving only a few strange fingerprints in the stone? We don't know, and maybe that's the beauty of it. Because once you start thinking this way, your perspective shifts. The story of existence stops being just about us, here, now, in this brief moment with glowing screens and electric lights. It becomes a story of layers. Civilizations, if they existed, would just be thin films on the surface of a very old world, each one rising, flourishing, collapsing, vanishing into dust and magma and time. Our entire history, the first tools, the first fires, the first cities, the first rockets, compresses into the thinnest possible line in the geological record. You, listening to this right now, are part of a flash, a spark between eons of darkness and silence. But within that spark, there is meaning. Whether or not there were others before us, we know this. We are here now. We can ask these questions. We can look at a rock, a star, a fossil, and wonder. Maybe no other civilization ever rose on this planet before ours. Maybe we are the first and only technological species the Earth has ever known. Or maybe far beneath our feet, in strata worn by time and pressure, the faintest traces of someone else are sleeping. Someone who once looked up at their own night sky and wondered if they were alone. Either way, the result is the same. We inherit a responsibility to treat this thin, fragile moment of intelligence as precious, to be better ancestors to whoever might come after, if anyone does. To leave behind not just chemical scars, but stories, knowledge, evidence that we tried to understand the universe we briefly woke up in. As you drift towards sleep, you can let your thoughts float backward and forward through time. Picture continents sliding past each other like slow-motion icebergs, forests rising and falling, seas advancing and retreating, meteorites, supervolcanoes, ice ages, and through it all occasional glimmers of awareness, minds that opened, looked around, and tried to make sense of it all, just like you're doing now. You're one small consciousness, in one brief century, on one world, in one galaxy among billions, and yet you carry within you the entire history of life on this planet. Every ancestor that survived, every catastrophe endured, every narrow escape. You're part of a chain that stretches back billions of years, and perhaps, just perhaps, is reaching forward into a future where other beings will one day wonder about you. For now, though, you don't have to solve any of it. You don't have to answer the Silurian hypothesis. You only have to rest. If you enjoyed drifting through deep time with me tonight, you can gently tap like, or leave a comment. Maybe tell us where in the world you're listening from, where on this ancient planet you're falling asleep. If you'd like to hear more journeys like this, you can subscribe so you don't miss the next one. And if you feel called to support the channel a little more, you can even join our membership here on YouTube. That's completely optional, only if it feels right for you. Your presence, your curiosity, and your quiet attention are already more than enough. Now, let the timelines fade. Let the ancient oceans grow still. Let the distant civilizations, real or imagined, dim into the background. Feel the weight of your body sink into the bed, the slow rhythm of your breathing, like waves on a very old shore. You're safe. You're part of this vast story, and for tonight, your only task is to sleep. May your dreams wander through galaxies and ancient seas. May you drift gently through deep time. Good night.